So what I thought we would finish today is the last piece that is missing for the finite element method, which is the mapping and the assembly stage. We started with the mapping last time from the physical domain to the reference domain. And we're going to finish that part and then look at how we would assemble all these local contributions to basically assemble the full matrices, stiffness matrix and force vector. And then we have this matrix system that we can solve with a linear solver. For that, is that good so far? Shall we do that? And then I would say the second part will look into the homework. Mostly I thought the upcoming homework, so where we basically now apply the finite element method to the little example that we had. That we mostly look at that one. If you want, we can look at your notes. I saw some of you did actually hand in your notes where you worked out on a piece of paper the stiffness matrix computations. Or we look also back into the pseudospectral method. So you can tell me if you want that, we can quickly discuss this at the end as well. Is that okay? So let's try finish the theory part, then attack the finite element example, and then maybe discuss some previous homework. Is that okay? Good, let's get started. So let me share the screen. I will put down some more notes, but you should have the lecture notes about the finite element method. It's basically there already. So I just basically go through that again here on this the whiteboard. And so let me try and share that quickly with you. So now you should see the notes. And I put down what we basically ended with last time in our finite element part 2 section. So we ended up with the mapping between the physical domain and the reference domain. The mapping basically means we have a position X, which is somewhere in our 3D physical room. And now we're going to map that within that finite element to a reference element, which is in our reference domain. And there the position is then xi. So we basically want to have a mapping where we map X to position xi in the reference element. Then why are we going to do that? It's mostly because in the physical domain, the elements can all have different shapes, different sizes, different positions, etc. So you saw in your little homework where you basically had to compute the stiffness matrix elements, that if you do that in the physical domain, you have to keep track of all the boundaries of the elements, etc. And so this mapping tries and make this more elegant, because now we're going to compute the integral expressions always in that reference domain. All we have to keep track is this mapping, basically. So the mapping from the physical domain to the reference domain and the inverse mapping. So going back from position xi to position x again. And so this obviously has to exist, so the mapping has to be invertible. Would not be the case, for example, if the element, in this case, the 1D element, if XA and the XA plus 1 would be the same position. So basically having an element with 0 size. Then there is no mapping which is invertible, for example. The same can happen in 2D or 3D when you have elements which are not regular elements anymore because of some distortion effect, etc. So then the mapping might not be invertible anymore. And we're going to see how we can actually define that and find out if the mapping is invertible or not. But so let's start quickly with this simple example. So we have the physical domain, 1D, and then we're going to map to a reference domain between Xi1 and Xi2. That's our two endpoints. And just by convenience, we set these endpoints always to -1 and 1. Good, and then what we were looking for is a linear mapping. So let me quickly put that down where we stopped last time. So we found a linear mapping.
Professor, I have a question about the
Yeah.
degrees of freedom. Those are like normal modes or something like that?
The D. So think of each point, each grid point, having now a degree of freedom, basically, which we have to determine. So the solution on each grid point has a degree of freedom, which we try and solve for. And for the finite element method, it basically comes to this finding the coefficients D, the dA coefficients. Those determine what the solution or the field will be exactly at that grid point location. Does that answer your question?
Yes, thanks.
Okay. Good. For the linear mapping, we found that. Some more questions?
Yeah, I'm just wondering that now if we have one element, it means that we have only one freedom. And if we have two, then we have two freedom, right? So does that mean that if we wanted to cut the 0 to 1 to two parts, so we have I mean the freedom means that you can put the cut point and everywhere.
So if we only have one element, in principle, we have 2 degrees of freedom. We have 2 nodes,
yes,
2 endpoints. That will make 2 degrees of freedom. On each node, basically, we are free to move basically our solution. But now, because we had these boundary conditions, the boundary condition imposes that we have a fixed value on one end, for example. That's the Dirichlet boundary. And that takes away that degree of freedom. So we are not free to move that point anymore, but it's fixed by the boundary condition. That's why at the end we have this one, like the degrees of freedom are then the number n, which is the number of elements in our case. But in a general way, you would have one element, 2 points. We use linear shape functions. They have 2 endpoints. And we have on both nodes, we have a degree of freedom. So that will make 2 degrees of freedom basically for this element, for one element. Now we take away 1 degree of freedom because we fix that solution with the Dirichlet boundary. That's a bit the confusing part in our example. But the example is chosen such that you see how that Dirichlet boundary then basically can be accommodated by a finite element method. What we could also do is we allow for these 2 degrees of freedom to be free, basically. So we determine those, but then impose that 1 degree of freedom always has to be the boundary value, for example.
Okay, but as you mentioned in last lecture, if we have 2 elements, the degree is 2.
That's because of the boundary.
We have 3 nodes. Huh?
Right, that's because of the boundary condition.
Okay.
So in principle, with 2 elements, you have 3 nodal points, 3 nodes. And if there would be no boundary condition, then we would have 3 degrees of freedom, D1, D2, D3. Those are the coefficients for our expansion. So then we would have our function approximation is then for n equal 1 to 3 in this case. dn times our shape functions, nn. And so in a general way, that will go to over all the nodal points, basically. But now we impose that degree of freedom by the boundary condition. Let's say this u at 1 has to be equal to q. Then one way of doing basically it is just now by having 2 shape functions. And this n plus 1 plus q times n plus 1 shape function. Where this one has to be 1 at the boundary. And these ones here, they have to be 0 at the boundary. Because our test function w will vanish at that point. That's it. We choose that test function because of the boundary condition we have. So now here, you see we only have 2 degrees of freedom. Well, if we wouldn't have the boundary condition, we would have 3 degrees of freedom. So in particular, it's the Dirichlet boundary condition. It's not the Newman boundary condition. It would be a Newman boundary condition. It's still free to move, so we still have a degree of freedom on that point. That's a bit the confusing part in our example. So the example we chose has this Dirichlet boundary, which makes here the numbers a bit different. The number of shape functions and the number of degrees of freedom that we have, and so forth. Is it a bit clearer now?
Yes, it's clear.
Okay.
So, sorry, so each element has this boundary condition, right? This is not the global view. Or is it?
No, this would be a global view.
Okay.
So in this case, we have 2 elements, element 1 and element 2. And the boundary condition only affect element 2, not element 1.
Yeah, okay, thanks.
Good. For this mapping, don't think of the boundary condition yet. Just think of a general element that goes from xa to xa plus 1. And we want to map that to a reference element. It goes from -1 to 1. Doesn't matter if the element is at the beginning, somewhere in the middle, or at the other boundary at the end. So just a general case. Good, let me quickly get rid of that. How do I do that? Good. Trying to clean up here. So let me put down the linear mapping. So the linear mapping is xi of x, which if it's a linear one, we can write it as 2x minus xa minus xa plus 1 divided by the element size ha. And the inverse would be x of xi, which would be 1/2 over ha times xi plus xa plus xa plus 1. So xi of x determines what is position xi in the reference domain or the reference element. X of xi brings us back basically if we have xi, what would be the actual position x in the physical domain. Good. We stopped here last time. So the two shape functions that we still have to define. So the two linear shape functions for this reference element are also linear. So our linear shape functions so we can write them as an A of xi now. So they are defined in the reference domain. It's 1/2 1 plus xi A, which is either the left or right point, times xi the position. And here A is 1 or 2. Xi A or xi 1 would be -1, and xi 2 would be +1. So the idea of having our reference element goes from -1 to 1. This would be xi1, this would be xi2. And then we have a shape function n1, would be this one, linear shape functions. So n1 of xi, and then the second shape function would be n2 of xi. So these are now defined in our reference domain for the reference element. And so the mapping now.
Professor?
Yeah?
Is this in a equation defined, or I mean, how does it come
A
from?
is 1 or 2. It's just a way of
Yeah.
writing it in a compact form. Instead
But
of A, we say it again.
How does the shape function come from?
We
I
define
mean,
it. we define
okay.
to have linear shape functions.
Okay.
And so we want to have the linear shape functions such that one is 1 at the left boundary and the other is 1 at the right boundary. So they have to have this form. And so our mapping x of xi, we can write this now in terms of these two shape functions, where we have xa times na of xi. Good, clear so far? So why are we doing this? So let's go back to the stiffness matrix. So let's go back to the stiffness matrix. And you saw the stiffness matrix elements, we can write them as our bilinear functional A for two functions, W and U, which is defined as going from 0 to, let's say, L of the derivative of W times the derivative of U. Integrate over the domain, physical domain L. So these are basically the contributions that we want to compute and calculate for two functions. And for the stiffness matrix, the two functions are the shape functions that we had, NA and NB, for example. So what we can do is basically split this up and say, well, this is the same as when we compute these integrals over all the elements. Well, now the boundaries of the integral depend on what the element is. And then have W, the derivative, times the derivative of U dx. So this would be still using the finite elements in the physical domain. But just once we have the domain discretized into elements, then we can write the integral as the sum over the contributions from each element. And so now comes the step into the reference domain. So we can write this integral also as the sum over all elements. But now we go from the reference domain. So we are now in the reference element, which goes from -1 to 1. Then having the derivatives, the functions. And since we do this mapping, we have this additional term of the mapping, the derivative of the mapping with respect to xi, and can integrate over xi. So this is now integrating in the reference domain or the reference element. So the derivative of the mapping, this x with respect to psi, that is also called the Jacobian. So how does that look like? Well, we know what the mapping is. Let's put it here again. The mapping we had is this sum over xa times the shape functions in the reference element. And so what's the derivative of that? So x with respect to psi is going to be the sum of xa times the derivative with respect to psi of the shape functions na. And so what we see is that the derivative of u with respect to x, we can write this as the sum of our degree of freedom dA times the derivative with respect to psi of the shape function in the reference domain times the inverse of the Jacobian. So you know this is psi with respect to x. And so if the inverse of the Jacobian is not defined, then the mapping is not invertible. So by looking at the Jacobian, we can see if the mapping is invertible or not, if we can use it or not. And if the Jacobian doesn't exist or is not invertible, that means we have some issues with the meshing that we have. Because there is no mapping possible from reference to physical and from physical to reference domain. So what do we get now? When we use these reference elements for the integrations. So we have our bilinear form, W and U. Which is now the sum over the elements E, where we integrate from -1 to +1 within the reference element. And now we have these derivatives of NA and NB with respect to psi times the Jacobian or the inverse of the Jacobian over d psi. But so look at the shape functions. So NA of psi. So we set out using these linear shape functions. So you can easily You can easily write down what the derivatives are and what this integral actually looks like. So this becomes the sum over E, and then it becomes minus 1 to the power of A plus B times 1 over the element size, HE. So you see, we do evaluate what this integral is. We evaluate what the derivatives of these linear shape functions is. We can do that. We know the mapping. And then we can evaluate exactly what these integrals are. So we can do that analytically here, in this case. And so what do we get now for these local contributions? So we can write now the local stiffness contribution for element E is this matrix 1 over the element size, HE, and the matrix looks like that. And so this is now the stiffness matrix. But at a local level. And so you see now the stiffness matrix calculation at the local level is much simpler. As soon as we know what the element size is, HE, we can very easily just write down the local contribution for that element. So now we have all these local contributions. The only difficulty is now basically assemble all these local contributions at the right place to construct our global stiffness matrix. So let's do that, called the assembly stage. So the assembling part allows us to move back from the local level to the global one. Or if you want, that's the physical level. And for this assembly stage, it often is convenient to define a matrix which brings us, or which defines for each local element and nodal point in the reference level, what is the global reference point in the global mesh. And it's called the location matrix. So let's define the location matrix. This is just convenient for the assembly stage to do that. and we just call it LM for local matrix. And then we have our local nodal point A and the element E. You can write this as then being defined either for is equal to E if A is 1, or E plus 1 if A is 2. So A here, that's our local degree of freedom. And E, that's the element number. And when we define it this way, then it gives us basically the global matrix index for that local point. So let's try and write this down. So to provide the global matrix index. So we can write it as this table, for example, where we have the two local degrees of freedom, xi1 and xi2. So that's these two nodes, -1 and +1. And then if we define it this way, the location matrix, then this would be 1 for element 1. This would be 2, element 2. Then it continues, the next element would be 2 and 3. And so on, to have basically E and E plus 1 until we get to element n. And then there is no n plus 1 degree of freedom because of the boundary condition, so that's just 0. So that would be our location matrix. And with this location matrix, we can then write the assembly stage. Well, the assembly can be written as the following. So we have the contribution to the global stiffness matrix, that's the contribution at E, E, E plus 1, E plus 1, E, and plus 1, E plus 1. That's the indexing in the global matrix. And the assembly means we add then to that existing index, or these existing values that we already have at these positions, the local contribution, which is always our key 1, 1, and that's for element E, 1, 2, 2, 1, and 2, 2. And that's our local element contribution. So the same we can do for the force vector. So we have Fe, Fe plus 1, where we add to the existing ones the local contribution. And to basically make sure that in our case at the last element we have the right contribution. So at the last element we have the stiffness matrix element K and N, and here this is this local contribution from the N element, the local element 1 1 from that one, and the same for the force vector, that's Fn, and here it's basically the contribution from the local force contribution at 1. So this is a bit maybe a new way of putting this down. So it's often easier to understand it by a simple example. So think of these contributions here, the stiffness matrix. So let's assume we would have, in our case, 5 elements. So having element 1, 2, 3, 4, 5. Then the nodal points we have are n plus 1. But we impose here the boundary condition. And so then the global matrix would look like K11, K12, 22, 21, 23, 33, and K4. So that would be the global stiffness matrix. We would have 4 degrees of freedom. Oh, sorry, it's 4 elements with this example. Yeah, let's not confuse ourselves. 4 elements, 4 degrees of freedom, but 5 nodal points, but we impose a boundary condition on the last one. So the global stiffness matrix goes from K11 till K44. And you see we would add now these, in order to compute what these elements are of the global stiffness, we compute the local element stiffness matrix for each element. And then we would have these contributions from the first element. Let's use a different color. Second element. Third element. And fourth element. Don't have colors anymore. So for example, look at the global stiffness index K22. K22 will have two contributions from two elements. It has a contribution from element 1, where it's going to be the local element K22, and it will have a contribution from the second element from the local index K11. So that's the right side of writing it. It's just trying to put these things at the right place. When we assemble now the global stiffness matrix, when we have all these local element contributions. Is that clear? So when you focus, for example, on this element, it will have a contribution from element 1 and element 2 because they share this global degree of freedom. And then from element 4, for example, you see the only nodal point that has a degree of freedom is the one on the left side. So we will have a contribution into K44 from the fourth element and from the third element. But the fourth element has no more contribution there. It's 0 because of the boundary condition. See, these are the local matrix. So if we select, say, element 4, then the contribution to the global one would be this thing here. So think of Kn, that becomes K40, K44, sorry, K40, K04, and K00. Because 5 is not a degree of freedom, so we put 5, 0. And that means all these contributions are 0. Doesn't count. The only actual valid contribution is this K44 coming from this local contribution K11 in the fourth element. So it's a bit, it looks a bit complicated at the beginning. This location matrix and the way we assemble things. It's just trying to put this into like a machine language or an algorithmic language, which makes it possible to just easily write it down such that we can update the global stiffness matrix. The same is for the force vector, the force contribution. So we'd have two force contribution in principle on both nodal points from the reference element, F1 and F2. So we can basically compute these and assemble as well. So let's make a quick example here to further make sure that we understand this. Let's say with two elements. So n is 2. Then we have the global stiffness matrix for our example. And keep in mind that we always have this boundary condition considered already. So the global one, capital K, is then just K11, K12, K21, and K22. That's the global stiffness matrix. That's the goal. That's the matrix that we want to construct. And once we have that matrix plus the force vector, we can then just easily solve for the degrees of freedom using this matrix form. So then what are the local contributions? So we have two elements, element 1, element 2. So K11, the global one, has these two contributions, the local one from element 1 plus the local one from element 2. How do I write that? Well, let's quickly use the first contribution. That would be K1 from element 1 and K22 from element 1. And now we would have in principle this local contribution from the second element. But in this case, it's not, still a bit tricky. It's not quite right the way I'm writing it. Let's say, so this is going to be the local contribution from element 1, but there is no contribution from element 2 for that. Then for 1, 2, the same. It's only a local contribution from element 1, but no contribution from element 2. But then with K22, we do have these two contributions. So we have the local contribution K22 from element 1, but now it's the local contribution K11 from element 2. So that makes it a bit confusing when writing here a local. Let me use here still global. Assume this is like a global index. So you can think of the matrix of having these contributions from two elements, but now because it's a boundary condition applied, we have the first element contribution is here, and the second element contribution would be this part. But because we have this boundary condition imposed, makes it 0 for the K33 for this last nodal point. So we only have 2 degrees of freedom in our example. And so K22 here has a shared node between element 1 and element 2, but in element 2 it's in the reference element, it's on the left node, the contribution. While in element 1 it's on the right node, the element contribution. So here it's K22 that comes from the right node, and here it's K11 that comes from the left node. So what are these contributions? We have them here. So those are our local level contributions. So let's see, for example, K11. That would be 1 over H1. We have 1. This would be 1 over H1 times minus 1. And then here we would have K22 from 1 is 1 over H1 plus K11 from element 2, that would be 1 over H2. And if you want, if we know that the elements would all have the same size, we could just easily write this. Like the element size is the same for H1 and H2. Then the global matrix would just be, well, 1 over H, or this H of the elements, with this contribution two for the K22 element. So this would be the global stiffness matrix. Is the example, is it clear? Good. You see, the elegant part is this one here. It's very easy to write down what the stiffness matrix contribution is at the local level. Once we have the element size, HE, the stiffness matrix can then be easily computed, and we can also assemble it very quickly into the global stiffness matrix. So it's much easier than keeping track of all these integrals, which might have all these different boundaries of the element in the physical domain. So I would say we go to the homework, where we now apply this method to the diffusion equation, the steady state diffusion equation. I'll quickly show you the slides about that example, and then that will be your homework for next week to implement now the finite element method for that little example. So I stop here with this. Is okay? Okay.
Yes.
Good. And the idea was to show you these slides here about the new homework. I call it homework 5. So the slides here, again, they basically just summarize the equation and the approach with the finite element method. And you see the steady state diffusion equation here? Good. So we start with the steady state diffusion equation and the boundary conditions. And so at boundary 1, that's the Dirichlet boundary. We impose what the temperature is. And on the left boundary at point 0, we have a Newman boundary condition. And then you can play a bit with these boundary conditions, especially with the force term F here. You can either set it to 0 or 1, for example. Good. So we write down the weak form of the equation on top. We expand now our test function and the temperature field into our basis functions, NA, and then we have this additional n+1 basis function because of the boundary condition. And so the unknowns are these dA coefficients. Once we have these unknowns determined and solved, then we know what the temperature field T fixes at any position. So when we use these expansions, we put this into the weak form and then find these expressions. Basically, you have on the left side, you have the stiffness matrix expression. Then comes the boundary term and the force term. So we looked at that at the very beginning of the introduction of the method. So you can write this in terms of bilinear functionals and functionals if you want. What it comes to is basically having this global stiffness matrix, the KAB, and the force vector FA. And then we can put this into this matrix form, K times D, where D is the vector with the degrees of freedom, which are unknown, is equal to the force. And then you can solve this for D by inverting K and bring it over to the other side. So what we do is now then consider this mapping. So we map from the physical domain to the reference domain. And here the J, that's the Jacobian that we just saw today. So you integrate over the domain, which in this case goes from 0 to 1. It's our physical domain. Or we could say it goes from 0 to L, for example, of a function G. Once we have that discretized into a set of finite elements, then we can take the sum over all these contributions from each element. And then each element is going to be mapped into our reference element. So that's how then the integral would look like using the Jacobian expression. So in this last expression where we sum over all elements from -1 to 1, where is the geometry of our problem? You see, we lost basically where the element is. So before we had all these integrals with the actual element positions that we had to evaluate. But now with this mapping, we always integrate between -1 and 1. So where is the information from the actual shape of the mesh? Do you have an idea?
In the middle?
No, not really. You mean G?
What's the question again, sorry?
So when you look at the integral expression, the very last one over the reference element, where do we account for the actual position of the element in the physical space? Where is that information? If you look at the integral expression in the middle or on the left side, 0, 1, that's the physical domain. Then we integrate over the physical elements, the finite elements in the physical space. So there the integral boundaries are determined where the element actually lies. But in the last integral, we don't have that anymore. So where did that information go?
The Jacobian, I think.
Right. It's captured by the Jacobian now. So the whole geometry is basically now mapped through the Jacobian. That is like keeping the information of the actual space of the physical dimensions. So keep that in mind. We still have that information, but now it's basically encapsulated by the Jacobian. Good. So here now we look at the integral values at the local level. So it's all between -1 and 1, where we define the shape function, where we compute what the local element contribution is for the stiffness matrix, is KAB contributions. And so we can easily evaluate what these integrals are for these linear shape functions between -1 and 1, and have then the matrix form written at the bottom here, where the element information is now within the element size, basically. That's the only thing that differs from one element to another. The same is for the force vector. You can figure out what are these contributions, the local contributions for the force vector. You can do the same thing. You look at it from a local level perspective, and then you have these terms you see either for the first and last element, depending on where we impose the boundaries. And then you have the local matrix form for the force vector. Okay. And then you have to do the assembly, basically, the assembling of the global matrices and the global vector. And for that, we can use this location matrix, for example, the way it's defined here. And then for the code example here is giving you how you could basically assemble the stiffness matrix by taking now these local element contribution and putting it all together into the global stiffness matrix. You can do the same for the force vector. And now we have the global system, global matrix form. And then solving it, you can just use a linear solver to find what the D vector is. So with that, you're almost done. And the example should look something like that. So once you have your finite-element method coded up with the template code that I provide you, then you should find solutions like that. On top, you have 10 elements. At the bottom, you only have 2 elements. And we can compare this against the exact solution, for example, for this problem. So you see, by increasing the number of elements, your approximation of the solution becomes better, because you also increase the degrees of freedom now. Good. That's the homework example for next week. So I'll put this again on GitHub, and you will have the template of this. Provided as MATLAB code. Now, do you prefer Python or MATLAB? At the moment, I have it as MATLAB, but I could provide you a template in Python as well, and then you can choose. Will I do that? Yeah, why not?
Yeah.
So maybe you saw with the previous homework, when you do it in MATLAB, it's a bit quite a bit faster actually when we try and make these simulations of waves propagating. When I do it in Python with NumPy, it takes much longer, much slower. Here for this example, it's a steady state solution, so it doesn't make much difference. So maybe I put then as well a Python template for that. And then you can decide whatever you like more. So let me see if I can open up the homework PDF. Just to quickly show you, there's not much more information. You will have the slides I just showed you as a helper material. Then this is the problem set, which just describes the homework. So you have the diffusion equation, the boundary condition, the analytical solution as well, and then just the different steps in order to solve it with a finite element approach. And here the only, let's say, playful part comes in with the number of elements that you can play around with, and with the force term, this f of x term, which you can either set to 0 or 1, and see how that affects the solution of the steady state. So that's very short and simple. For for the template, I can quickly try and show you that as well. See if I find it here. Good. So this will be a homework 5 template about the steady state heat equation or diffusion equation. Top you have the number of elements which you can play with. Then it sets out again the discretization, number of points, and number of elements. We have the boundary conditions, the force factor is a constant, either 0 or 1. Can play around with that one. And then we have here the stiffness matrix and the force vector, and that's basically where you will then start coding. So you can think of putting up your location matrix, and then compute the local stiffness matrix and the right-hand side of the force vector, right-hand side vector. Do the assembly part, construct the global stiffness matrix and global force vector, and then solve it within MATLAB. And I left this open. It's very simple how you can solve such a linear system in MATLAB. The same in Python, actually. It's a very simple command. And then the rest is plotting. So again, there's not much coding involved here. It's just the tricky part is here, setting it up correctly to construct the global stiffness matrix and the force vector contributions. But together with the slides, it shouldn't be too much of a headache to do that. We'll figure that out quickly. Is it clear? Good. I would say you work on it till next week, Thursday. See if you can hand it in by Wednesday so we can look at it on Thursday. Is that good?
Yes.
Yes.
So do you want to look into your previous homeworks? Shall we quickly discuss that in a few minutes? Or to me, there's not much discussion about writing out what the stiffness contributions are. You basically have the solution, so unless you couldn't find out what that is, we can discuss it now. Otherwise, you just email me questions about that part. For the pseudospectral homework, that's homework 4. Is there still a question about that homework? So the main part is this one here. Where especially this thing here with the multiplication, so doing the derivative in the Fourier domain. We can do it this way in MATLAB, for example. So you do an FFT first. You take the derivative in the Fourier domain by multiplying with I times k, basically. And then doing the inverse Fourier transform of the field. That gives you the derivative now. In this case, the derivative of the temperature field T with respect to the position X. And then the same for the velocities, or here it's the stresses, is not the temperatures, the stress T. We have a stress, velocity stress formulation, sorry. The same here, multiplication with IK in the Fourier domain, and then taking the inverse Fourier transform. At the end, update basically your field, velocity and stress. So I put this on Dropbox. You have that on Dropbox. You can compare with your. Now the boundary condition, I don't have a good solution to that one. So you see when we impose this, for example, for Dirichlet, and this for the Newman boundary, at some point it doesn't look that nice anymore because it becomes more and more unstable. There's more and more ringing when we impose these boundary conditions. And that's an issue with the pseudospectral method using the Fourier transform. It's not easy to impose a boundary condition for that method. It can lead to instabilities. So if we would need to solve that stability issue, it becomes more involved actually. And so why, that's one of the reasons why, for example, the Chebyshev transform was suggested. It's more convenient to impose the free surface condition or absorbing boundary condition using a Chebyshev transform. But that would be beyond the scope of this class. It's really just, class is meant as an introduction into these methods. Now you had the introduction, now you see where there are still some problems venturing around, so if you feel free to like dig deeper and go into that topic. Good. Everything clear? Know what to do with the homework? Pretty much clear about the finite element approach?
Yes.
Good. So we have our next class on Sunday, I guess?
Yes.
And we're going to continue with the examples. That's okay. So we will look into the non-steady state diffusion equation. See how that can be incorporated, adding a time dependence to the equation. There's no much magic in doing that. It's fairly straightforward. Like based on our experience with the pseudo-spectral method, you saw that the time dependence, we just use the finite difference schemes for the time differences, time differencing, and use here for the spatial derivatives, then use the finite element approach that we had figured out now. So that's about what I want to do next Sunday.
Professor.
Yeah.
I have question for the pseudospectral.
Mm-hmm.
When I apply the boundary condition in T1 is equal to 0, but Tnx minus 1 is equal to 0, so not Tnx equal to 0, but Nx minus 1 is equal to 0. It work.
That can be a stabilization. It can help stabilizing the solution. You're right.
Yes. Okay. Thank you.
It's something to try out with this stabilization, right? But yeah, it's still tricky because the FFT is it sees the field as a periodic field. And so by kind of imposing now a boundary to it, the FFT has issues with that by imposing it. And when you use the neighboring point and set it to 0, for example, as well, that can help in stabilizing it. So it can work for one type of boundary, not necessarily for the other type of boundary. Right. But a good observation, yeah. No, good. Then I wish you a good weekend. Here it's already weekend starting. And then see each other Sunday again. Good. Then wish you stay safe, stay healthy,
You.
and see you soon on Sunday. Good.
Thank you.
See you.
Thank you, Professor.
Bye, everyone.
Bye.
Hi, guys.